A very good morning, my dear students. In the previous lecture, we have started discussing the sequential logic circuits, and in previous lecture, we have mainly concentrated on discussing NAND latch and NOR latches, and also the clock input, different types of clocks that we are going to apply to any sequential logic circuit, like level triggering and edge triggering circuits. In today's lecture, we will mainly concentrate on discussing the clocked RS flip-flop. Clocked RS flip-flop, and also in addition to this, we will also discuss something about preset and clear inputs. Okay, these are the two inputs which we can apply to any flip-flop or to any sequential logic circuit asynchronously. So these two inputs are called asynchronous inputs, preset and clear inputs, and we will discuss about the clocked RS flip-flop and also preset and clear asynchronous inputs in this lecture. So upon completion of this lecture, you'll be able to know or understand RS flip-flop construction and its working and preset and clear inputs. In the previous class, we have seen what is a latch, what is meant by a flip-flop, what is the difference between flip-flop and latch. So the difference between flip-flop and latch is what? Flip-flop is edge triggered and latch is level triggered. Both are happens to be the storage 1-bit storage element. So latch is also a 1-bit storage element, or flip-flop is also a 1-bit storage element, but the clock, applying the clock is different to flip-flop and latch. Flip-flop is edge triggered and latch is level triggered. And also sequential circuit. What is the definition of sequential circuit? Sequential circuit is defined as the output not only depends upon the present inputs but also on previous outputs. In the case of sequential logic circuits, the output not only depends upon the present inputs but also on previous outputs. If you observe the block diagram of a sequential circuit, it consists of first a combinational logic circuit, and you'll be having some feedback. Some portion of the output is again feedback as input, like this feedback block, you are calling it a memory element, and these are the inputs. And this is the output of sequential logic circuit. Okay, so this is a combinational logic circuit, and this is a memory element, and some portion of output is again fed back to the input, and inputs are applied. So output of any sequential logic circuit not only depends upon the present input but also on previous outputs. So this is the basic definition of sequential logic circuit. Next we'll have a discussion on clocked RS flip-flop. A latch is similar to a flip-flop. It can reside in either of two stable states. What are the two stable states here? Logic 1 and logic 0. Logic 1 and logic 0 are the two stable states. So NAND or NOR latches are also called as RS flip-flop. So whatever we have discussed in the previous lecture, that is NAND latch or NOR latch. NAND latch is nothing but two cross-coupled NAND gates. NOR latch is constructed with the help of NAND latch is constructed with the help of two cross-coupled NAND gates like this. So this is the circuit diagram of NAND latch. This is circuit diagram of NAND latch, and this won't be there. Okay, so this is a simple circuit diagram of NAND latch through which you can able to implement RS flip-flop. Okay, and similarly, if you replace this NAND gates with NOR gates, that becomes NOR latch. So NAND or NOR latches are also called RS flip-flop. Symbol of RS flip-flop is like this. It will be having two inputs. It will be having two inputs, R and S, and two outputs which are complementary to each other, Q and Q bar. And S stands for here set, and R stands for here reset. So RS flip-flop is also known as set reset flip-flop. RS flip-flop is also known as set reset flip-flop. Okay. RS flip-flop is also known as set reset flip-flop. So this is the basic symbol of RS flip-flop without applying any clock. So depending upon inputs applied, that means if you are applying 0 inputs, you'll be getting invalid output. Okay, so this is one combination, and for 0 1 combination you'll be getting output as 0 because R is 1, that means resetting. So output will be 0 and its complement will be 1. Only for 1 0 combination, you'll be getting the output Q as 1 and Q bar as 0. Okay, that means since S, that means set input is 1, you are setting the flip-flop. Setting the flip-flop means making the output of the flip-flop to be equal to 1, and obviously its complement will be equal to 0. So if you consider the last combination 1 1, the output will be as it is, Q and Q bar. So whatever the output is there, that will be again same as the previous output. So output will be no change for 1 1 combination of SR inputs. For 1 1 combination of SR inputs, you'll be getting the Q as no change. Okay, or you can also call the state of the flip-flop as hold state. That means whatever the previous output is there, that is hold, that will be hold by the flip-flop when R is equal to 1 and S is equal to 1. So for 1 1 combination of R and S inputs, you will be getting the output as hold state or no change in the output. Whatever the previous output is there, that will be continued for R is equal to 1 and S is equal to 1 combination. So this is the basic logic symbol of RS flip-flop. Next we will now see the extension of RS flip-flop, basic RS flip-flop, that is without applying clock. So now we will observe the operation of RS flip-flop with the application of clock signal. We have seen in the previous lecture how to apply the clock to a flip-flop in different ways, like level triggered or edge triggering. Level triggering means whenever the clock is in high state, during that instant of time, if some inputs are changed, then it will be reflected in the output. Similarly, whenever this clock signal is at low signal, that means logic low, that means in that instant, during that instant of time where the clock signal is low, if at all, if any inputs are changing, then the output will be changing. That is level triggered, positive level triggered and negative level triggered. If you observe with the help of a circuit diagram, you can show the level triggered like this. Let us say this is the clock signal you are applying to a flip-flop. So level triggering means this is positive level triggering and this is negative level triggering. Positive level triggering, negative level triggering, positive level triggering and negative level triggering. So whenever during this instant of time, whenever the input changes, it will be reflected in the output of the flip-flop. So this is known as level triggering, positive level triggering and negative level triggering. This is positive level triggering and this is negative level triggering. In a similar manner, if you observe the edge triggering, again I am considering the same clock pulse like this, in which the output of the flip-flop will be checked only at the instance where the clock is changing its state from logic 0 to logic 1 or logic 1 to logic 0. This is known as positive edge triggering and this is known as negative edge triggering. So whenever the clock is changing its state from 0 to 1, whenever the clock is changing its state from 0 to 1, whenever the clock is changing its state from 0 to 1, that is called, at that instant of time, if you are checking the output of the flip-flop, that is called positive edge triggering. Similarly, if you are checking the status of the output, if you are checking the output of the flip-flop whenever the clock is changing its state from logic 1 to logic 0, whenever the clock is changing its state from logic 1 to 0, if you are checking the output at that instant of time, that means you are applying negative edge triggering. That means you are applying negative edge triggering. That is the meaning of positive and negative edge triggering clocks. So these are the different ways of applying a clock signal to any sequential logic circuit or to any flip-flop. So now we will now discuss the clocked RS flip-flop. That means in addition to the R and S inputs to the flip-flop, you also have the another input called as clock. You also have the another input called as clock. Okay, so we will see, this is the circuit diagram of clocked RS flip-flop using NAND gates. Okay, so earlier in the previous lecture we have discussed about this circuit, which you are calling it as RS flip-flop. Okay, this is nothing but without clock. It is without clock. Now we will discuss the circuit diagram, the extension of that, whatever we have seen in the previous lecture, that will be extended with the help of clock. So here I am, in addition to the S and R inputs, in addition to the S and R inputs, you also have the another input called as clock signal. You also have the another input called as clock signal, which are applied to both the NAND gates like this. Okay, and the circuit will be responding to the inputs. The circuit will be responding to the inputs only when clock is high. Only when clock is high. Let us assume the status of the circuit when clock is equal to 0 and clock is equal to 1. What happens if clock is equal to 0? That means to the first and second NAND gates, let us assume these are first and second NAND gates and these are third and fourth NAND gates of circuit. So to the first and second NAND gates, 0 will be one of the input. 0 will be one of the input, so that the output of the first and second NAND gates will be equal to 1. The output of the first and second NAND gates will be equal to 1. So when 1 and 1 are available at the third and fourth NAND gates as one of the inputs, then what will be the output? We have seen in the last class, output will be no change. So there will be no change in the output. That is, you can also call that state as hold state. So the output will be in hold state whenever clock is equal to 0. So if you are not applying any clock, that is the meaning of clock is equal to 0. If you are not applying any clock, then the output of RS flip-flop will be equal to its previous state only. The present output of RS flip-flop will be equal to its previous output state. So if I assume Qn plus 1 is the present output state, then I can say Qn is the previous output state. So when clock is equal to 0, the present output of the flip-flop will be equal to its previous output. Qn plus 1 is equal to Qn. So that is the meaning of making clock is equal to 0. So whenever clock is equal to 0, irrespective of the inputs, SR inputs, the output will be maintained in the hold state. The output will be, present output will be holding the previous output. Present output will be holding the previous output. That means there is no change in the output state. There is no change in the output state of the flip-flop when you are making clock is equal to 0. So whenever clock is equal to 0, irrespective of the S and R inputs, whenever clock is equal to 0, irrespective of the S and R inputs, output will be in the hold state only. Hold state means present output is equal to previous output. Qn plus 1 is equal to Qn, where Qn plus 1 is the present output state and Qn happens to be the previous output state. So present output state is equal to previous output state. There is no change in the output unless until you are applying any clock. Okay, so when clock is equal to 0, irrespective of the R and S inputs, output will be in the hold state only. Okay, and the circuit will be responding to the inputs, and the circuit will be responding to the inputs. The circuit will be responding to the inputs S and R only when clock is equal to 1. The circuit will be responding to the inputs only when clock is equal to 1. It is because for the first and second NAND gates, when clock input is equal to 1, what happens? The output of the first and second NAND gates depends upon the other input. Okay, since one of the input is 1, output will be equal to S bar, here R bar you will be getting. Okay, it will be S into 1 whole bar, which is nothing but S bar, which is R into 1 whole bar, which is R bar. S bar and R bar will be available at the outputs, at the inputs of third and fourth NAND gates, and correspondingly you will be getting the output. So depending upon the value of S and R, depending upon the logic level of S and R, the output will be responding, the output will be produced based on the different combinations of input S and R inputs. Okay, so that means whenever clock is equal to 1, whenever clock is equal to 1, then only the output will be changing its state depending upon the S and R inputs, depending upon the S and R inputs. That is the meaning of clocked SR flip-flop. Unless until you are not applying any clock, there will be no change in the output of flip-flop. And whenever clock is equal to 1, then only depending upon the input combination, the output will be produced for any flip-flop. So this is nothing but clocked RS flip-flop, and this is the symbol of RS flip-flop. In the previous lecture we have seen what type of clock I am applying here. Here I am applying positive level triggered clock. Here I am applying positive level triggered clock. In the previous section itself, in the previous lecture itself, we have seen this stands for positive level and this stands for negative level, and this stands for positive edge, and this stands for negative edge. Okay, so out of this, here this type of clock I am applying here. That means what type of clock I am applying here is positive level triggered clock. It is positive level triggered clock I am applying to the clocked RS flip flop. I am applying to the clocked RS flip flop. Okay, so this is the block diagram of a RS flip flop, and it is clocked. This is the block diagram of a clocked RS flip flop, clocked SR flip flop. Next we will see whenever clock is equal to 0, whenever clock is equal to 0, what happens to the output? Output, there is no change in the output. There is no change in the output because whenever clock is equal to 0, irrespective of the other inputs, what are the other inputs here? R and S. So irrespective of the other inputs, output of the first and second AND gates will be equal to 1 only. So whenever 1 is available, there is no change in the output. That means hold state or no change in the output, or no change in the output. That means whenever clock is equal to 0, there is no change in the output, no change in the output. Whenever clock is equal to 0, there is no change in the output. So irrespective of the input combinations of S and R, there is no change in the output of flip-flop. So whenever clock is equal to 1, then flip-flop is enabled. Then flip-flop is enabled. What do you mean by enabling the flip-flop? That means responding to its different input combinations. So output of the flip-flop will be produced depending upon the different input combinations of S and R inputs whenever clock is equal to 1. So you can also say clock will be acting as like an enable for a flip-flop, enable pin for a flip-flop. Whenever clock is equal to 0, output will be, there is no change in the output. Whenever clock is equal to 1, then only output will be, flip-flop will be enabled, so that depending upon the different input combinations, the output will be produced. Depending upon the different input combinations of R and S inputs, the output will be produced. Okay, so here I can say clock can be used as an enable input. Clock can be used as an enable input for a flip-flop. So whenever clock is equal to 1, flip-flop is enabled, so that output of the flip-flop depends upon the different input combinations of flip-flop, that is R and S inputs. Okay, so this is the truth table of clocked RS flip-flop. We will see the operation of this flip-flop. Whenever clock is equal to 1, let us say initially S is equal to 0, S is equal to 0 and R is equal to 0, and clock is equal to 1. So what happens? let us say this is first, second, third and fourth. So when S is equal to 0 and R is equal to 0, what happens? Output of the first NAND gate will be equal to 1. Output of second NAND gate is also equal to 1. Okay, so one of the inputs to the third and fourth NAND gates will be 1 1. So for 1 1 combination, output will be what? Uh, for 1 1 combination, so here q bar is available, so 1 into q bar, that is q, so that means no change in the output, no change or hold state, no change or hold state. So whenever S is equal to 0 and R is equal to 0, when clock is equal to 1, output will be no change. That means there is no change in the output of the flip-flop for R is equal to 0 and S is equal to 0, and when flip-flop is enabled, that means clock is equal to 1. So clock is equal to 1 is by default, in order to make the dependence of the output on the different combinations of input. Okay, so whenever I am saying output of the flip-flop will be changing depending upon the input combinations, that is by defaultly the clock is made as 1. That is by default clock is made as 1. That you have to remember. Okay, so for 0 0 combination of S and R inputs, what will be the output you are getting? You will be getting, there is no change in the output. That means the output is in the hold state. The output is in the hold state. That means if Q is equal to 0, if Q is equal to 0, then output will be equal to 0. If Q is equal to 1, then output will be equal to 1. So whatever the previous state is there, that will be continued even for S is equal to 0 and R is equal to 0 combination. So this is one combination. We will see the second combination. What is the second combination? R is equal to 0 and S is equal to 1. If R is equal to 0 and S is equal to 1, if you observe, the output of the second NAND gate will be equal to 1, because one of the input is 0. Since one of the input for the second NAND gate is 1, output of the second NAND gate will be equal to 1. Okay, and what about the first NAND gate? Since 1 1 are applied as inputs to the first NAND gate, the output of first NAND gate will be equal to 0. So since 0 is one of the input to the third NAND gate, the Q output will become 0 and Q bar output should become 1. So for R is equal to 0 and S is equal to 1 combination, for R is equal to 0 and S is equal to 1 combination, what you will be getting? Q output will be equal to 1. For R is equal to 0 and S is equal to 1, for 1 1 combination, output of first NAND gate will be equal to 0. For 0 1 combination, output of second NAND gate will be equal to 1. So since for the third NAND gate, one of the input is 0, output will be equal to 1 and its complementary output will be equal to 0. So for R is equal to 0 and S is equal to 1, you will be getting the output as 1. That means you are setting the flip-flop. You are setting the flip-flop. So that's why S stands for set. S stands for set. So whenever S is equal to 1, that means you are setting the flip-flop. What do you mean by setting the flip-flop? Making the output of the flip-flop to be equal to 1. Making the output of the flip-flop to be equal to 1. That's the meaning of making set input as 1. Since R is equal to 0, you are not resetting, you are only setting the flip-flop, so output will be equal to 1 and its complement will be equal to 0. So this is for R is equal to 0 and S is equal to 1 combination. Similarly, for R is equal to 1 and S is equal to 0, we need to observe the circuit operation. For R is equal to 1 and S is equal to 0, since 0 1 is available at the input of first NAND gate, the output will be equal to 1. The output of the first NAND gate will be equal to 1, and similarly the output of the second NAND gate will be equal to 0, because both the inputs are 1. So clock is anyhow 1. So since for the third and fourth NAND gates, for the fourth NAND gate, one of the input is 0, that means Q bar is equal to 1, so Q should be equal to 0. So that 1 will be available here. So 1 1 combination of the NAND input will give you the output of 0. So for R is equal to 1 and S is equal to 0, you will be getting the output as 0. That means now the flip-flop is in reset state, because you are making reset input is equal to 1. So whenever you are resetting the flip-flop, the output should be equal to 0. The output of the flip-flop should be equal to 0. Okay, and its complement will be equal to 1. So that is the meaning of resetting the flip-flop. That means making the R input as high, then you will be getting the output as 0. This is the third combination, R is equal to 1 and S is equal to 0. Similarly, I am considering the fourth combination, R is equal to 1 and S is equal to 1. So what happens if R is equal to 1 and S is equal to 1? Since anyhow clock is equal to 1, the outputs of first and second AND gates will be equal to zeros, because for the first and second AND gates all the inputs happens to be 1, then the output of first and second AND gates will be equal to 0. So whenever 0 and 0 are applied, Q should be equal to 1 and Q bar should be equal to 1, which is unpredictable, which is not defined, which is not defined. Okay, so or you can say it is invalid, it is invalid, or there is one particular term, the output is in racing, the output is in racing. So this is the technical term which you can use for invalid output of a flip-flop. So in RS flip-flop, racing will be occurring for R is equal to 1 and S is equal to 1 combination of inputs. In RS flip-flop, racing will be there when the input combination is R is equal to 1 and S is equal to 1. Racing is nothing but unpredictable output, or indefined output, or invalid output. Okay, so invalid output is available in RS flip-flop when R is equal to 1 and S is equal to 1. Racing occurs for the input combination of R is equal to 1 and S is equal to 1. So these are the different combinations of inputs. So if you mention all those combinations in a truth table, it looks like this. So whenever, if there is no clock applied, that means whenever clock is equal to 0, so irrespective of the R and S inputs, the output will be in the output will be no change. That means the operation of mode of operation for flip-flop is hold state. Then the flip-flop is in hold state. Whenever there is no clock applied to the flip-flop, what happens? Output will be no change and operation will be hold operation. The mode of operation will be hold. That means the flip-flop is in hold state. Whatever the output is there earlier before applying the clock, that will be continued since you are not applying any clock signal. So whenever clock is equal to 0, irrespective of the input combinations, there is no change in the output. That means I can write Qn plus 1 is equal to Qn, where Qn plus 1 is equal to present output and Qn is previous output. And present output is equal to previous output means there is no change in the state of the output. That is when clock is equal to 0. Similarly, when clock is equal to 1, and then that means whenever you are making clock input as 1 for a flip-flop, that means that flip-flop is enabled. What do you mean by enabling the flip-flop? Depending upon the input combination, the output of the flip-flop will be produced. Depending upon the input combination of R and S inputs, the various outputs will be produced. Okay, so this clock, I can say it is an enable input for a flip-flop. Clock is called as enable input for a flip-flop. Whenever clock is 1, that means flip-flop is enabled, so that the output of the flip-flop depends upon the input combinations of the flip-flop. The output of the flip-flop depends upon the input combinations of the flip-flop. So whenever clock is equal to 1 and R is equal to 0 and S is equal to 0, what happens? For R is equal to 0 and S is equal to 0, there will be no change in the outputs. Again, the flip-flop is in hold state. For R is equal to 0 and S is equal to 0 combination. Similarly, if you observe the second combination, that is R is equal to 0 and S is equal to 1, you are making S is equal to 1 means output will be equal to 1 and its complement will be equal to 0. That means the flip-flop is in set state. So here S input stands for set input, R input stands for reset input. Whenever set input is equal to 1, you are setting the flip-flop. What do you mean by setting the flip-flop? Making the output of the flip-flop to be equal to 1. That's why Q is becoming 1 and its complement output Q bar is becoming 0, so that the mode of operation is set. That means the flip-flop is in set state. Similarly, for the third combination, R is equal to 1 and S is equal to 0. For the third combination, R is equal to 1 and S is equal to 0. That means reset input is 1. So you are resetting the flip-flop. That means making the output Q to be equal to 0, and so that its complement will be equal to 1 and the mode of operation is reset. That means the flip-flop is in reset state. The flip-flop is in reset state because you are making reset input as 1. Because you are making reset input as 1. So whenever reset input is 1, then what will happen? The output of the flip-flop will be equal to 0 irrespective of its previous state. Irrespective of its previous state. So whenever you are resetting the flip-flop, irrespective of its previous output state, so Qn plus 1 Qn plus 1 is equal to 0 irrespective of previous output. What is its previous output? That is Qn irrespective of it. That means Qn plus 1 is independent of Qn plus 1 is independent of Q naught for the two combinations, 0 1 combination and 1 0 combination. 0 1 combination and 1 0 combination. So whenever R is equal to 0 and S is equal to 1, whenever R is equal to 0 and S is equal to 1, what happens? You are setting the flip-flop, so making the output of the flip-flop to be equal to 1, so that the flip-flop is in set state. Similarly, for R is equal to 1 and S is equal to 0, that means you are resetting the flip-flop, so making the output to be equal to 0, and the mode of operation of flip-flop is in reset state. Okay. So for R is equal to 0 and S is equal to 1, and for R is equal to 1 and S is equal to 0, you will be getting the distinct outputs. So for 0 1 combination, you are getting the output as 1, and for 1 0 combination, you are getting the output as 0 irrespective of its previous output state. Irrespective of its previous output state. This you have to remember, because for 0 0 combination, output depends upon previous output. Present output depends upon previous output. That means there is no change in the output state. So if earlier, if Qn is 0, Qn plus 1 is also 0. If Qn is 1, then Qn plus 1 is also 1 in first case, for R is equal to 0 and S is equal to 0. And for R is equal to 0 and S is equal to 1, irrespective of its previous output, irrespective of Qn, the Qn plus 1 will be always equal to 1. That is the meaning. And for R is equal to 1 and S is equal to 0, irrespective of Qn plus 1 is equal to 0. You are resetting the flip-flop, and for 0 1 you are resetting the flip-flop. So these are the three combinations. If you observe the last combination, 1 1 combination of R and S inputs, racing occurs. That means this is invalid. Mode of operation is invalid or prohibited. So the unpredictable state of output is known as race. Race is defined as the unpredictable state of the output is called race. So for R is equal to 1 and S is equal to 1 combination, the racing occurs for RS flip-flop. For R is equal to 1 and S is equal to 1 combination, racing occurs for RS flip-flop. That means the 1 1 combination of RS inputs is invalid inputs for RS flip-flop. Is invalid inputs for RS flip-flop, because when you are giving when clock is applied and R and S are equal to 1, you cannot define the output of the flip-flop. That's why the mode of operation is prohibited. That is nothing but unpredictable state of output is known as race. Unpredictable state of output is known as race. Okay, so this is the truth table. This is the truth table of clocked RS flip-flop. Truth table of clocked RS flip-flop. So when there is no clock applied, irrespective of the input combinations, output will be equal to its present output will be equal to previous output. That means there is no change in the state of the output, so that the mode of operation, you can call it as hold. And when clock is applied and for different input combinations, the output will be produced. So for 0 0 combination of R and S inputs, again there is no change in the output state. That means Qn plus 1 is equal to Qn, which is nothing but which is equal to present state is equal to its previous present output state is equal to previous output state, and mode of operation of flip-flop is hold state. It is holding the output. And for r is equal to 0 and s is equal to 1, output will be equal to 1, q is equal to 1 irrespective of its previous output state. So present output state will be equal to 1 irrespective of its previous output state. Then the mode of operation of flip-flop is set state. And for r is equal to 1 and s is equal to 0, qn plus 1 is equal to 0 irrespective of its qn. So present output state is always equal to 0 irrespective of its previous output state, so that the mode of operation you can call it as a reset state. And for r is equal to 1 and s is equal to 1 combination, there is no output. That means output is invalid output. So that unpredictable state of the output is known as race. Unpredictable state of the output is known as race. So this is something about the clocked RS flip-flop, its circuit diagram, and also its truth table after discussing the working of RS flip-flop, clocked RS flip-flop. Okay. If you observe the timing diagram for applying different input combinations, okay. If you observe, let us say I am considering I am considering the clock signal like this. Okay, I am considering negative edge triggered clock. That is a negative edge triggered clock. So what happens if I am applying negative edge triggered clock? That means during this instant of time, whenever clock is changing its state from logic 1 to logic 0, at that instant of time, it will be checking for output. It will be checking the inputs, and correspondingly it will be producing the output. So during negative edge triggering clock pulses, during negative edge triggering clock pulses, during negative edge triggering clock pulses, whenever clock is changing its state from, sorry, all these are negative edge triggering clock pulses. So at the first negative going edge, before that s is equal to 0 and r is equal to 0. So when r is equal to 0 and s is equal to 0, the output will be in its previous state. Let us say initial state of the output is 0. Okay, so before applying the first negative going clock pulse, r is becoming 1 and s is again 0. So since r is equal to 1 and since s is equal to 1 and r is equal to 0, that means you are setting the flip-flop. So output is changed from 0 to 1 at this instant of time. Output is changed from 0 to 1 at this instant of time, where you are applying the negative going clock pulse, negative edge triggered clock pulse. Okay, so now at this instant of time, output is changing its state from logic 0 to logic 1, and at the second negative going pulse, again s is equal to 1 and r is equal to 0. When s is equal to 1 and r is equal to 0, again output will be equal to 1. Even for this also, output will be equal to 1. And here the output is, the s input is changing its state from logic 1 to logic 0. Now what will happen, this logic 1 to logic 0 transition is applied after the application of this third negative going edge triggered clock. So that means this third negative going edge triggered clock also, the output will be equal to 1. And whenever next clock pulse is applied, that is fourth negative going edge triggered, fourth negative edge triggered clock pulse is applied, there the output, the inputs are s is equal to 0 and r is equal to 1. So for s is equal to 0 and r is equal to 1, the output will be equal to 0, because since you are resetting the flip-flop, that means r is equal to 1, so making the output to be equal to 0 from that instant of time. So after the application of fourth negative edge triggering clock pulse, what will happen? So before the application of fourth negative edge triggering clock pulse, the inputs are s is equal to 0 and r is equal to 1. So since r is equal to 1, the output should be changing its state from logic 1 to logic 0. Okay, and after that also what happens, again s is equal to 0 and r is equal to 1, because that means q is equal to 0 will be maintained like that only. Okay, So this is the clock diagram or timing diagram of a clocked SR flip-flop. Timing diagram of a clocked SR flip-flop. So for different input combinations, for 0 0 you'll be getting the output as 0, and for 1 0 you'll be getting the output as 1, and for 0 1 you'll be getting the output as 0. Okay, so for 0 0 input combinations you'll be getting the output as 0, and for 1 0 input combination, that means S is equal to 1 means making the output to be equal to 1, and for R is equal to 1 means making the output to be equal to 0. Okay, so this is a simple timing diagram for a clocked RS flip flop. Simple timing diagram for a clocked RS flip flop. So this is something about clocked RS flip flop. Next we will see what is the need of preset and clear inputs. To set or reset the flip flop, we have to use the inputs to the flip flops. To set or reset the flip flop, we have to use the inputs to the flip flops, because if you observe SR flip flop, if S is equal to 0 and R is equal to 1, you will be getting Qn plus 1 is equal to 0, and for S is equal to 1 and R is equal to 0, you will be getting the Qn plus 1 is equal to 1. So this is called reset and this is called set. Okay, so for setting the flip flop, S should be equal to 1, and for resetting the flip flop, R should be equal to 1. So that means to reset or set the flip flop, we have to use the inputs to the flip flops. In a computer, it would be very inconvenient or difficult to set or reset each and every flip flop independently. Okay, whatever I have discussed till now is specific to the flip flop itself. In order to reset or set the flip flop, we need to make its corresponding input, uh, either S is equal to 1 or R is equal to 1. Depending upon that, either the output of the flip flop will be setted or resetted. That means making the output to be equal to 1 means setting the flip flop, making the output to be equal to 0 means resetting the flip flop. And this has to be done for each and every flip flop independently, and this process is very tedious or very inconvenient in a computer, because in a computer there are lakhs of flip-flops. And it is not possible to set or reset all the flip-flops independently. In a computer, since there are lakhs of flip-flops available, it is impossible, in fact I can say it is impossible to set or reset each and every flip-flop independently. That's why there exists some asynchronous inputs called as preset and clear inputs, so that whenever you are presetting the circuit, that means all the flip-flops outputs will become 1. That is the meaning of presetting. So when the power is switched on, flip-flops may come up in random states. To set or reset all the flip-flops at a time, we use asynchronous inputs, which are called as preset and clear inputs. So preset and clear inputs are called asynchronous inputs, which can override all the inputs. So that is the main advantage of using preset and clear asynchronous inputs. So that is the need of preset and clear inputs. So to set or reset the flip-flop, we have to use the inputs to the flip-flop. In a computer, since lakhs of flip-flops are available, it would be it is impossible to set or reset each and every flip-flop independently. And when the power is switched on, the flip-flops may come up with random output states. So to set or reset all the flip-flops at a time, we need to use asynchronous inputs, which are called as preset and clear inputs. So these preset and clear inputs are called asynchronous inputs, which can override all the inputs. So independent of your whatever the inputs you are applying, the all those inputs are independent whenever you are applying asynchronous inputs. So when asynchronous inputs are coming into picture for all the flip-flop circuits, what will happen? The output will be either presetted or cleared, irrespective of the inputs. That is the meaning of to set or reset all the flip-flops at a time, we use asynchronous inputs, which are called as preset and clear inputs, which can override all the inputs. So the preset and clear data are called direct or asynchronous inputs. Asynchronous inputs, other name is direct inputs, and the examples for direct or asynchronous inputs is preset and clear. preset and clear. It is more or less equal to set and reset only. Set is nothing but preset, reset is nothing but clear, clearing the inputs, clearing the output of the flip-flop or setting the output of the flip-flop. That is the meaning of preset and clear. So the preset and clear data are called direct or asynchronous input. Preset and clear data are called direct or asynchronous inputs. These inputs are not in synchronism with the clock. So whatever the inputs you are applying, whatever the asynchronous inputs you are applying, they are independent of clock. They are independent of clock. Even with without even with the absence of clock, these asynchronous inputs are active for any flip-flop. Even with the absence of clock, you can apply these asynchronous inputs, preset and clear. These preset and clear inputs may be applied at any time in between clock pulses. So these preset and clear inputs can be applied at any time in between clock pulses. That means preset and clear inputs are independent of clock pulses. Preset and clear inputs are independent of clock pulses. The output of flip-flop is set to 1 by activating the preset input. Okay, so what do you mean by activating the preset input? Making the output of the flip-flop to be equal to 1. That means setting the flip-flop. So the output of the flip-flop is set to 1, or making the output of the flip-flop to be equal to 1 by activating the preset input. So preset input is whenever preset input is activated, the output of the flip-flop should be equal to 1 irrespective of its input combination and irrespective of the application of clock pulse. That you need to remember. Irrespective of the application of clock pulse or irrespective of the input combinations applied at that particular flip-flop, if you are activating the preset input, the output will be always equal to 1 irrespective of the input combinations as well as the application of clock pulse. Similarly, the output of the flip-flop is reset to 0 by activating the clear input. On the other hand, clear input is mainly used to reset the flip-flop. What do you mean by resetting the flip-flop? Making the output of the flip-flop to be equal to 0. Making the output of the flip-flop to be equal to 0 is called resetting the flip-flop, and that can be done by activating the clear input. So whenever you are activating the clear input, the output of the flip-flop will be resetted to 0 irrespective of its input combinations as well as the application of clock pulse. Whether the clock pulse is applied or not, whether you are applying any combination of inputs, irrespective of all those things, if clear input is enabled, then the output of the flip-flop will be equal to 0. That is the advantage of preset and clear inputs, which are called as direct inputs or asynchronous inputs. Next we will move on to the quiz. Name the flip-flop which has a racing problem. Racing problem will be available in which type of flip-flop? That is RS flip-flop. Just now we have seen in the discussion of in the working of clocked RS flip-flop. For R is equal to 1 and S is equal to 1 combination, you will be getting the racing problem. So racing problem occurs in RS flip-flop. Option A is correct. Next, universal flip-flop is JK flip-flop. This we are going to discuss it in the next lecture. For the time being, remember, universal logic gates as NAND and NOR gates, and universal logic circuit as multiplexer in the case of combinational logic circuits, and in the case of sequential logic circuits, universal flip-flop happens to be JK flip-flop. JK flip-flop happens to be the universal flip-flop because by using JK flip-flop, any other flip-flop can be realized. Whether it is D or T or RS flip-flop. That's why JK flip-flop is a universal flip-flop. Option D is correct. Overall summary, we have discussed about RS flip-flop, its construction with NAND gates and truth table. So we have mainly discussed about clocked RS flip-flop. Clocked RS flip-flop we have seen. Okay. So RS flip-flop construction with NAND gates and its truth table also we have seen, and in addition to that we have also discussed about need for preset and clear inputs. So in order to make the output of the flip-flop to be equal to 0 or 1, we can apply preset and clear inputs irrespective of the application of clock pulse and irrespective of the input of the flip-flops. Okay. Next, frequently asked questions. Draw the schematic symbol and truth table of RS flip-flop and explain. So you need to draw the truth table and also symbol, schematic symbol of RS flip-flop, and you need to explain for different input combinations and for clock how the circuit is responding and what will be the output for different input combinations. Similarly, explain the operation of clocked RS flip-flop with a neat timing diagram. So with the help of timing diagram also, you can able to explain the operation of clocked RS flip-flop, which we have seen, and also explain the need for preset and clear inputs. This also we have seen in this lecture. So this completes the today's lecture. In today's lecture, we have mainly concentrated on circuit diagram and truth table and working of clocked RS flip-flop, and also the state and also the need for preset and clear inputs. In the next lecture, we will mainly concentrate on JK flip-flop. Okay. Thank you. Thank you for listening.